Let's take a closer look at integrating over our solid object to get the rotational inertia. I like to spend some time on this because we're also going to do this to find the center of mass of a solid object. And next quarter in electricity and magnetism, you're going to do this again, except it's not going to be mass density, it's going to be charge density, and you're going to be integrating over the charge distribution to find electric fields. So it's important you get some understanding of the math involved here. If I have a one-dimensional object, a thin rod, and it has some total mass m, and it's going to have some length L, how would we find the mass density if it's a uniform density? We divide the total mass by the total length. Now, if we have a two-dimensional object, a flat sheet like a sheet of paper, it would also have some total mass m, but we now have two dimensions we have to keep track of, not just length, we have area that we have to account for. And what would the mass density be if it's uniform mass density? The total mass over the total area. And if we have a three-dimensional object, it might also have some total mass m. But now what are we concerned with? Volume V. And what would the mass density be? It would be the mass per unit volume. So the symbol we use for density for a one-dimensional object is lambda. And lambda has units of mass, kilograms, over length, meters, kilograms per meter. We use a different symbol for the mass density of a two-dimensional object. We use sigma. And sigma has units of kilograms per square meter. And we use a different symbol for the mass density of a three-dimensional object. We use the Greek letter rho, and that has kilograms per meter cubed for units. I know it's a little confusing that we use different symbols for one-dimensional, two-dimensional, and three-dimensional density, but I think it comes from the fact that each one of these has different units, so that's why we use different symbols. Let's take a look at this example. We're going to calculate I for a rod rotating about its center point, a uniform rod. So we already did the one where it's rotating about its end point. And you should be picking up some intuition about this. We have a rod here, and if you grab it in the center and you try to rotate it, how does that feel? Is it easy? Hard? Now you move your hand all the way to the end of the rod and you try to rotate it now. Is it easier? Is it harder? How does that feel? In other words, do you expect our answer to this problem to be more or less than the answer we got to the one in the previous video? In the previous video, we did a rod rotating about its end point. That would be this situation. Now we're going to do the rod rotating about its center point. And I hope you see that this answer should be less, because the mass is in closer to the axis of rotation. It should be much easier to get this rod rotating and to stop it from rotating than if we're holding it at the end of the rod. When you have all this mass at the end, that really contributes a lot to the rotational inertia because it's got its distance squared. We'll start with our formula. The rotational inertia, or the moment of inertia, is equal to the integral of r squared dm. So dm is the mass of some arbitrary little chunk here. Just pick one. I always draw a picture, pick some arbitrary chunk. Don't pick a special location. Don't pick the center of the rod. Don't pick the little dm at the axis of rotation. Don't pick the one at the end of the rod. Some odd arbitrary location. Now I'm going to assign an x-axis here. This end of the rod is at L over 2. And the other end of my rod is at x equals negative L over 2. That means that the distance to dm is r, and I'm just going to call that x because I've aligned this with the x-axis. And this distance, the thickness, the width of my little mass element dm is equal to dx. Let me clean this up a little bit. I've got x and dx for those distances. So I say, well, what is r? R is going to be x. What is dm? dm is the mass density lambda for a one-dimensional object multiplied by the length dx. This is always true. If lambda is constant, I can plug in the total mass over the total length. I guess I should have given you here. If we know the total mass and the total length. Now I can plug these in. I get I is equal to the integral of x squared lambda dx. And I say, what are my limits of integration? I have to integrate over every little dm that makes up that rod. That means I'm starting all the way over here, and I'm adding up all the dm's along the way, all the way out to that end. So from negative L over 2 to positive L over 2. Now I ask myself, is lambda constant? If it is, it comes out of the integral. If it's not, I'm probably given some function for it, and I can just plug that function in here. And then it changes my integral slightly. In this case, it's constant. It comes out. I've got this 1/3 here. My lambda is the total mass over the total length. And I've got x cubed evaluated at L over 2. And minus, evaluated at negative L over 2 is going to give me a plus. And that turns out to be 1/12 ml squared.